Okay, so here's our notes on conic sections. So if you kind of got the idea about an ellipse, conic sections have a similar properties in the sense that they have two foci. They also will have two directrices, each one on the other side of the vertex, the vertices of your hyperbola. So a hyperbola looks sort of like two parabolas going in opposite directions. And the basic definition of a hyperbola is based on the tension between this distance from one focus to a point on one of your branches to the other focus. So when that distance, d3 minus d2, it remains constant, the difference is 2a being the distance between the two vertices. Now this is no longer called a major axis like it was in an ellipse, it's called the transverse axis. And then you have something that you don't actually see, but does exist, and that is there is an axis that goes down the middle. That is going to be called the conjugate axis. And we'll be using that to draw our hyperbolas. All right, so we're not going to actually use that definition, but it is how we define a hyperbola. Okay, so in terms of what the standard form looks like, it's very much like an ellipse, so it will be translated to a center of h over a squared. But now instead of plus, you're going to have a minus y minus k squared over b squared equals 1. A is always going to remain with the positive term. So unlike an ellipse where A stays with the greater term, now A stays with the positive term. So when the x term is positive, that means your hyperbola is coming off of the x-axis. So the center is HK. You have two vertices, so those are like the vertices of the, if you think of these like parabolas. So that means you go out to H and back and forth a distance of K, but you're still here. I don't actually ever really memorize these. It's much easier just to draw it, but I'll put these down anyway. Your foci is also still a distance of C from wherever your center is. That's always going to be a distance of C. So in this orientation, it'll be H plus or minus C and K. The length of the transverse axis is 2a. Your conjugate axis, which we will use to draw the hyperbola, is 2b. And there is a Pythagorean relationship, and in this case, it's straight up Pythagorean. A squared plus b squared equals c squared. With the ellipse, it was a squared minus b squared. So that's the relationship of your a, your b, and the c, the distance to the focus. Now, something that the hyperbola has that the ellipses don't, and it helps us draw it, is two asymptotes that cross through the center, and they have an equation. They help determine how wide or how narrow your graph is going to be. And the equation of those asymptotes is really pretty easy. So you start off y minus k, and on this side we'll have x minus h. So you just keep the same translation that you would for the center, and the slope, because notice one is going in the positive, one is in the negative, is the rise over the run. So remember, the rise is in the y direction, the run is in the x direction. But what determines that rise over the run is going to be the x and the y. Sorry, I was busy doing that. So this is a distance of b, and this is a distance of a. So if you look underneath your y, that's going to be the b in this case. So rise over run, b over a. Okay, and it's also going to be obvious when we draw it because you can just basically do rise over run and you can figure it out. All right, so that's when you have a horizontal hyperbola because it's going off of the x-axis. When we have a vertical one, so that's when you are going to be going off of the y-axis, you're going up and you're going down, everything is basically the same, except now you are going to have the y term is going to be positive, so it gets the a squared minus x minus h squared over b squared equals 1. So again, a is always with a positive term. You still have a center of hk, but now your vertices are going to be up and down from wherever the k is. So it'll be k plus or minus a. Your foci will be hk plus or minus c. And length of the transverse now is still 2a, because a now is going to go in this direction. And the length of your conjugate will be 2b, and that's now going to go off in the x direction. The equation of your asymptotes is still going to be y minus k equals plus or minus, and we'll have x minus h. But now your rise over your run, notice the rise, what's underneath the y value always represents the rise. So now it's going to be a over b. So that's a over b to get to the equation of the line. All right, so those are our equations. It looks kind of like an ellipse, the equation. It's just that now you have a minus instead of a plus. So let's go ahead and do an example here. So we have x minus 2 squared over 16 minus y plus 1 squared over 36 equals 1. So we know that our center is going to be at 2, negative 1. And because x is positive, I know my graph will have that orientation. So we'll go to 2, negative 1. And we're going to draw ourselves a box based on what a and b are. So we know that a is 4 and b is 6. So in the x direction, 1, 2, 3, 4, 1, 2, 3, 4. In the y direction, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So notice it doesn't matter who is bigger or smaller now, like it did with the ellipse. It's all about which term is positive and which term is negative. So you draw this little box here. And that box is what allows you to identify your asymptotes because they are the diagonals. So you sit here and draw your diagonals, which are your asymptotes. So you always want to, well, I'm going to always ask to see your asymptotes. And then here are your vertices, because we know we're going in the x direction. So we just follow the asymptotes. So try not to draw anything too skinny if your asymptotes are very wide. And that is how you would draw your hyperbola. I do want to add to that, I will often ask you for the equation of the asymptote. So let's go ahead and do that. So notice I just look at the equation and I pull off the y plus 1 equals plus or minus. Down here we have the x minus 2, so there's your translation. And then the rise over the run is what's underneath the y over what's underneath the x. So that's going to be 6 over 4, which we could of course reduce to 3/2. All right, and that would give you the equation with the plus or minus in front. Okay, so let's talk a little bit about the eccentricity. If you remember from the ellipse, the eccentricity had exactly the same formula, except that it was always going to be between 0 and 1. And with a hyperbola, so where's the D2, where's the D1? So here you have your foci, and the D2 and D1. So D2 is the same one as we had before, but we had earlier on the other page, this was what we called D3. That's what we use to describe the definition. D1 is always this perpendicular distance from a point on the graph to the directrix, to one of the directrices, okay? So the relationship of D2, the ratio of D2 to D1 is what identifies how eccentric your graph is, how wide it is, how narrow it is. So it's going to be that proportional pull. And so if you notice, since D2 is always going to be greater than D1 in a hyperbola, that means E will always be greater than 1. So that's really all you need to know, is that if we tell you an eccentricity and the eccentricity happens to be greater than 1, you know we're talking about a hyperbola. If we tell you the E is like 0.5, then you know we're talking about an ellipse. If we tell you it's 0, you know we're talking about a circle. Okay? And like an ellipse, you have 4 different radii that we can identify. So when we talk about A is always going to be that distance to your vertex. And again, you have 2 vertices, but I'll draw it over here. B is always going to be what we call the distance to the on the conjugate axis, which only used to draw your box. It's not really a part of the actual graph. And then we have, of course, C. So here's my foci. That represents your focal radius. And then you have D. So D is going to be the distance to a directrix. And again, you usually have 2 directrices, but we're only drawing 1 there. Okay, so you have what is called the transverse radii. You have your conjugate radii. And you have your focal radii and your directrix radii. And again, this is not the kind of thing I'm going to worry about too much. My main goal is that you know how to graph them and how to manipulate the parts. Okay, so just like with the ellipse, we also have a property. So you have your E is greater than 1, and we have this D, remember D now is your distance to the directrix, equals A squared over C. It's actually exactly the same property as the ellipse, and it came from here, where if we use both of these and isolate D, so I can substitute in for A, and then isolate D, that's where this comes from. And again, I don't expect you to memorize those, but we talked about it with the ellipse, and it helps us if we're trying to find a particular distance, okay? So let's take a look at how we would use some of this. So we have this example here, 16x squared minus 9y squared equals 144. So the first thing that we want to do is put it into standard form. So that means we want to divide through by 144. So I'm going to have x squared minus y squared equals 1. And when I divide through, 16 divided by 144 makes 9. 9y squared divided by 144 is 16. So if I were to then, so obviously we know this is a hyperbola, not just because these are notes on hyperbolas, but because of that negative there. And it doesn't matter whether your coefficients are the same or not. We wrote the equation in standard form. The 4 radii, so we know that A is going to be 3, and that's what's right underneath the x. B is going to be 4, so that's right here. And since with a hyperbola, we know that A squared plus B squared equals C squared. 3 squared plus 4 squared we know is going to be 25. So in this case, C will be 5. And D, your directrix radii, well, that's where we would use D equals A squared over C. So that's going to be 9 over 5. I can draw 5. There we go. So 9/5. Okay. Let's go ahead. So there's your, and your eccentricity. Eccentricity is always C over A. So that's going to be 5/3. Notice that it's greater than 1 because it is a hyperbola. So let's go ahead and graph this. We have a center, in this case, of 0, 0, so this one's a little bit easier. So I'm going to go out to 3. We're going to go up to 4. We're going to draw the box. Then we draw our asymptotes. So here's the asymptotes. And then this one, again, the x is the squared term, so we're going to come off the x-axis. And your graph is going to look like that. And if I wanted to give the equation of the asymptotes, which I will usually ask for, now this one's going to be a straightforward y equals, because there's no translation, the rise over the run, so that was 4 over 3, so plus or minus 4/3 x would be the equation of my asymptotes. All right, so that's the end of part 1, because I don't want this to be super long. The next 2 pages I will do in Hyperbolas part 2. All right, welcome back. Here is Hyperbolas part 2, and we're going to start off with a review of how you graph a hyperbola. So notice in this first example up here, the x term now is negative, so I do know that my center is going to be -5, +4. The a value is going to be 3. That's underneath the y now, because this graph is going to go off in the vertical direction. I know that b is going to be a distance of 2. I know that c, which is your focal distance, is 9, so a squared plus b squared, so 9 plus 4. This will be the square root of 13. My directrix distance, a squared over c, will be 9 over square root of 13, and your eccentricity, which is c over a, is going to be the square root of 13 over 3, which again is greater than 1, so that helps us know that we have a hyperbola. So if I'm going to graph this, I will go to the center, so at -5, 1, 2, 3, 4, and I'm going to go in the y direction, 1, 2, 3, 1, 2, 3, and in the x direction, b. Draw the box, draw the asymptotes, and now, because this is in the y direction, we start up here and do our graph off in this direction. And here we go. Okay? And if I wanted to know the equation of the asymptotes, which I tend to want to ask, it'll still be y minus 4 equals plus or minus. The rise over the run is still under the y over under the x, because under the y is your rise over your run, and then x plus 5. And you do not have to simplify it or put it in y equals mx plus b form. I would just keep it in its translated form. Okay, now this next example is kind of interesting, because you are going to have to, just like with the ellipse we did these, do a little bit of your distance formula. So we're going to start off with, find the general and standard form, so this one's both, of the conic with focus at -2, 5. So let's go ahead, -2, 5. Now that's our focus, that's not a vertex. And the directrix is at y equals 2. So here's my directrix. And my eccentricity is e equals 2. All right, so we know we have a hyperbola because my e is greater than 1. And so what are we going to do here? We're going to use the fact that d2 equals e d1, but as I did in class, we're going to make this a little bit easier, because we're going to be using distance formula, and I don't like square roots, so we are going to square everything right here, so we don't have to do any square roots. All right, so what is d2? ed1, what are these terms? Okay, so what we're going to do is we are going to draw just a very rough, this has nothing to do, we have no idea where the actual graph is other than it goes around the vertex like this. Okay, so we're drawing, again, this is only one of the vertices, one of the foci, one of the directrix. We know the other one will be somewhere. We have no idea where. And so what we're going to do with that is we know that if I draw from the foci to a point on the graph and drop a perpendicular, This represents D2. This represents a point on my graph. This represents D1. And remember, this is the line y equals 2. And my foci here was -2, 5. So we're going to use our distance formula. So the distance of D2 is going to be, and again I'm going to square it, so I don't need to include my square root. It's going to be x minus a -2 squared plus y minus 5 squared. So that's D2 squared, that's just using your distance formula. And remember, the point here is going to be whatever x is going to be the same because we dropped perpendicularly. The y-coordinate will always be 2. So when I go to plug this in, my eccentricity they told me is 2, so this will become 2 squared. And d1 squared, well, x minus x is going to be 0, so I don't even need to write it. I'm just going to write y minus 2 squared, because the x minus x will just go away. Now the rest of this, to put it in general form, is really just foiling and collecting like terms. So I'm going to have here x squared plus 4x plus 4 plus y squared minus 10y plus 25 equals 4 times the quantity y squared minus 4y plus 4. So that's going to give me 4y squared minus 16y plus 16. And we basically want to set everything equal to 0. So let's see what we got here. We have x squared. That's still there. And I've got a y squared minus, so I have y squared minus 4y squared. So that's going to give me minus 3y squared. Then we combine our x, so I have, let's see, plus 4x. And then we're going to combine our y's. So there's a minus 10y, and I'll be adding to that 16y. So that gives me plus 6y. And now all I have left are my constants. So I have a 4, 25, so that's 29, minus 16, which is going to give me plus 13 equals 0. And that's what we call the general form. And this case, we also wanted to have it in standard form, which means we have to complete the square. So now we backtrack a little bit. We put all our x terms together, plus blank, then minus, we have to factor out a 3 here. So I'm going to have y squared, not plus, we want that to be a minus 2y. That's the tricky part of the parabolas, the hyperbolas, because you factored out a negative. You have to remember when you distribute it back through, so it changes that sign. But I'm still going to add something to both sides, and this will equal a negative 13 plus blank minus 3 times blank. So I have the same thing happening to both sides. Okay, I'm not quite sure what happened with those seconds, but so sorry. So this last page is going to deal with the parametric form of our hyperbola. Okay, so with the ellipse, you were using cosine squared plus sine squared equals 1 and manipulating that relationship. With the hyperbola, because you have the x squared minus y squared, you want something that has a minus in it but equal to 1. So the relationship we're going to use is the fact that 1 plus tangent squared equals secant squared. And since I want to isolate the 1, what we really have here is secant squared x minus tangent squared x equals 1. So when we're writing a hyperbola, the positive term is always going to go with the secant. The negative term will always go with the tangent. So there's no one always gets. It all depends on who's positive, who's negative. Just like who gets the A, who gets the B. All right, so how this is going to work, if it's a vertical, remember that means that your graph looks like this. So that means the y term would be the positive. So notice that y is getting the secant term here, and x is getting the tangent term. If it's horizontal, then notice the x is getting the secant term. And so the h and the k, your center's out in front, your dilation is a and b. I don't always look at it that way. Let's go ahead and look at how you would do this translation. So when I look at this, x is my negative term. So I'm going to take the x plus 1 over 4, and I know that because it's the negative term, is going to equal the tangent. I already got rid of my squared, so I've already taken the square root of both sides, okay? And now if I isolate x, so that means x is going to equal, I would multiply by 4 and subtract 1. So notice my h was out in front, so there's that h, and the 4 was the dilation factor. I would do the same thing, since y is the positive term, I'm just going to pull off the square root, so I know that y minus 3 over 5, since it's the positive term, I set it equal to secant, and I isolate y. So y is going to equal, multiply by 5 and add 3, 3 plus 5 secant. So you can see the k term sitting out in front, and 5 is the dilation factor. All right, so that's really all I would have to do to convert it into parametric form. And then this is just one last, how do you graph a hyperbola? So notice this is going to have the x term, well this is the term, the example from above. So it's a, what we call a vertical, because the y term is the positive. The center is still hk, negative 1, positive 3. A is going to be underneath the positive term, so that's going to be 5 in the y direction. B is 4. The asymptotes are going to be y minus 3 equals plus or minus underneath the y over the x, rise over run. So 5/4 x plus 1. And so to graph it, we go negative 1, 1, 2, 3. And that means 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4. 1, 2, 3, 4. And we draw the graph. Draw the asymptotes. And then since it's going in the y direction, here's your vertex. And then here is your other vertex. Okay, and that is the main idea of a hyperbola.